We are going to look at transformers and one of the two losses that it has. Um, the first one here is the core losses, and we know that those are fixed as long as we have rated voltage on them. So how much the core heats up due to the eddy currents and hysteresis. But the one that we don't know and we have to calculate are the copper losses. So that's what this is going to be looking at, is calculating the copper losses on a transformer. So I got this example here. We have a 5 kVA transformer. It's 240 to 120 single phase. The resistance of the H winding is 0.0 ohms. So I'll just put that here. So this is your H winding. 0.8 ohms. And the resistance of the secondary or the X windings here is 0.4 ohms. Okay. So what we're going to do is we're going to apply our formula. P is equal to I squared R. Okay. And so calculate how much heat these windings are going to give off, and in this case at full load. All right. So the first thing that we're going to have to do is we're going to figure out the I, the primary. It's rated primary current. So what would be the current through the primary at full load? Well, I'm going to use my full 5,000 VA. I'm going to divide it by my primary voltage of 240. And that is going to give me 20.8 amps. Okay. All right, so now I know the resistance of the primary, and I know the current flow through the primary at full load. I can calculate the I squared R losses. So P equals I, the primary, squared, so this is of the primary, times R, the primary. So we got 20.8 amps squared times 0.8 ohms. That would come to, where would we be at here? 346.112 watts. So we know that the primary copper is going to dissipate 346.112. And we can look at the secondary now. So the losses on the secondary due to copper losses, so Cu loss. So here we have to figure out the secondary current. So I, the secondary, same thing, 5,000 VA divided by this time 120 volts, and that should come to about 41.7 approximately amps. So put it in our formula, I squared of the secondary rated current times the resistance of the secondary. That comes to bracket 41.67 amp squared, I guess I don't need the bracket, times 0.4 ohms. All right, and that should come to approximately 695.556 watts. Now for the total losses, I just add up the total losses, PCU, of this transformer. So that's a total, both the primary and secondary. We just need to add 346.112 plus 695.556. So these numbers are a little bit exaggerated just for this. And then we add that up. That's 1,041.668 watts approximately. Okay, so that'd be our total copper losses if this transformer was at full load, just over 1,000 watts. So that's how we could calculate it if we know the resistance. The other way is we could just test this transformer. We do that closed circuit test or short circuit test, and we apply the voltage very slowly to the primary with an amp meter in the secondary, and then read our watt meter on the primary, and that will also tell us the combined copper loss of both the primary and secondary windings. Now, the question here I'm going to propose to you is, I'm going to take this same transformer, and what do you suspect this transformer's losses would be if I only loaded it up to half load? So half load, so 5,000 kVA is its full load. If I divide that by 2, so half load or 50% of it, we are only loading it up to 2500 VA this time. Well, so over here we had a 5000 VA load. Over here now we're only putting on 2500 VA. So that means the current is going to be about half going through. Okay, let's go ahead and calculate it at half load, and we are going to see what our new losses come to. All right, so compare it to our total losses at full load here. So if we're at half load, so we're going to go I, the primary, is going to be equal to 2500 VA divided by 240. That's going to come to about, where are we at here, 10.4 amps. I, the secondary, might as well calculate that. Same thing, 2 to 1, so, or 1, yeah, 2 to 1 transformer, 2500 VA divided by 120 this time. And that will be about that 20.8 again. So about double the current. All right, so using our VA formula. So the voltage ratio is a 2 to 1, so the current ratio is 1 to 2, so that makes sense. If we got 10.4 in the primary, we'll have 20.8 on the secondary. So the losses on the primary due to the copper, Cu loss, primary, that will be equal to 10.4 amps squared times our resistance of 0.8 ohms. And that will come to 86.528 approximately watts. And on the secondary here, the heat dissipated by the secondary winding, so Cu loss, secondary, the I is 20.8 squared times our resistance of 0.4, and that will come to about 173.056 watts. And so if we wanted the total loss here, Cu loss of this transformer total, we'd have to add these two up, and it would come to about 260 watts approximately. So roughly. So I just wanted you to look at these two numbers here, that the total at full load, the total watts loss, copper losses at full load is just over 1,000, so 1,041. But at half load, it's only 260. So it's roughly a quarter of what it would be. So why is that? Well, the losses are due to the square of the current. So the current has an exponential effect on it. The greater the current, the much more losses it is if it's exponential. So another way to do this is that if we said we're at half load here, or 50% load, right? Half load means 50%, and this works with whatever percentage. We could use 75% load, 80%, 60%. This works with every load. So if I know the full load copper losses is 1041.668, so full load is 1041.668, I can multiply that by whatever load I'm at, so 50%, which is 0.5, and square it. So if you square that percentage and multiply it by your full load copper losses, we will get the same value. All right, so punch in my calculator, 1041.668 times 0.5 squared, which is 0.25, 260 watts. All right, so just an easier way to get there. So if you're ever on a question that gives you, let's say you're doing a short circuit test, and it gives you a watt meter reading during the short circuit test of 1041 or some sort of wattage, and then it says calculate the half load copper losses, or the copper losses at 75%. I would just take that full load copper losses from my short circuit test and multiply it by my percentage load I'm at squared. So let's say in this example we did a 0.5. What would be the losses at, let's say, 75%? So if I want to know at 75%, what are my losses? Load, right? 75%, what are my losses? I would go, okay, well, full load copper losses. So CU, full load, times my percent load that I'm at, and square it. So in this case, 1041.668. And if I want to know at 75% load, I times it by 0.75 squared. 1041.668 times 0.75 squared equals 586 watts approximately at 3/4 load, or 75%. Okay, I'm going to do the next video you're going to see is I'm going to go over some efficiency examples. We'll see you there.